Okay, here's a video to briefly explain, and I'll make a document later on because I'm not really a big fan of videos in some ways. But to explain my little measurement apparatus for testing fans. Now, the guys at Igor Labs have a much more expensive and fancy one, but I've also noticed that some of their data is obviously not right for some reason. So I don't know what's going on there, but I can't really trust that data. So I'm trying to collect some of my own. Also, we have some other fans that we want to know about. They didn't test the P14 Max, for instance, or the iScale Extra. That data seems to have been collected a while ago, and it was from Germany. They have different availability of different fans and stuff. So what we're measuring here is 4 main parameters, and then a few minor ones. So we've got a Raspberry Pi Pico over here with two DPS310 sensors. They're absolute barometric pressure sensors, not differential sensors. So there's one hanging in the pipe there, and there's one outside measuring the ambient pressure. In order to compensate for the drift that occurs over time, we take a measurement before starting the test and during the test. So it's only a short time period between the two. I think all things considered, it's probably good to about 0.5 pascals, maybe 0.6, something like that. In any case, that's plenty for our purposes. We're talking about differences of from 8 to 40, usually, the actual measurement. So it is a little bit rough, but I did order a better sensor, and we'll get that, and maybe I'll just forget about the data that I collected from this round and use that instead. But I think this is probably fine. So then I attach the fan of concern to a plate, like this one. I have a couple different plates. These are from the energy recovery ventilator. It's got to be sucking air through the pipe, then blowing it out, because you got to have the same direction in both cases. And then I have it connected to the power supply. I adjust the voltage, record the voltage and current. I check the RPM. There's a little sticker on here. It's a retroreflective sticker. I use a laser tachometer, which is just a cheapy one, but you don't need much. And I measure the noise with this. It's a class 2 sound meter. They are calibrated. So they're not particularly expensive, but they are pretty solid, I think. It didn't come with a certificate, but it seems to be reliable. And they're not as precise as the class 1 meters, of course, but the class 1 meters are really expensive. And this is more than enough for what we need. Now, because the background noise is in the range of 40 decibels, and we are talking about noises in the range of 45 decibels and above at 1 meter, there's a bit of a problem. The signal isn't very strong compared to the noise, the background. So what I've been doing is I measure it both at 1 meter and also at 0.25 meters. So you get a much stronger signal. We can compare the fans with less noise in the data. And this is the flow restrictor. You need something to restrict the flow so that you can get measurements of different pressures and flows. I'm going to have to chop this in half. I have a whole bunch of these. These are the old heat exchangers from the energy recovery ventilator. But for now, I've just been putting it in the pipe. It goes in the pipe like that. Put it all the way in the same position every time. And then finally, last but not least, there is the anemometer. So this goes in the tube, and it goes always in the center. It has to be exactly in the center. I'm careful when I'm actually doing measurement. I'm not going to be careful now. And then I measured at various velocities a different depth, because there is actually a gradient between the wall of the pipe and the center of the pipe. The velocity is not the same all the way across the pipe. People often assume that it is, but it's not. And I actually found that the ratio of the average velocity to the velocity in the center was between 0.77 to 0.9 or so. So it's actually pretty significant, and that has to be factored in if you want to measure the actual volumetric flow. So yeah, this seems to be a good approach. I particularly like the flow restrictor because it's a nice laminar exit. You don't have, like, if you have a hole, if I had like a shutter, then that actually has a very significant impact on the aerodynamics of the fan blades, because the air would be going at a higher velocity in one region and hit the fan blades, and it also affects the noise and stuff. So the other thing is that this is deliberately hanging off the edge of the table. so that air can come in from all sides as it's being sucked in. That has, I'm pretty sure that would probably have a significant effect. So it doesn't seem fancy, but you don't really need much. I really like the idea of using water, but what I found was that the water would stick quite significantly to the edges of the pipe, um, the tube in the water manometer. Where's my water manometer? Oh, here it is. So if that tube was made out of some kind of transparent fluoropolymer, that would probably be a lot better. But I had to shake it and measure it carefully, and it was hard to get a good measurement. I think these digital sensors are actually going to be quite a bit better. They're a lot easier to read. I've been taking some measurements already, and to be honest, unfortunately, the P14 fan is a really good fan in terms of flow and noise. The iScale Extra is better in terms of flow and pressure at the same RPM, but it's actually probably because the blades are a little bit too close to the struts, and the struts are not curved in the same way as the P14 fan. The result is that it does make a buzzing noise, which is really annoying, and it does show up on the decibel meter. So that's too bad. But it's got ball bearings, so that's why I really like this one. It's also got very high maximal power, which is handy in some circumstances. So, yeah, I don't know if there's anything else I can say about this. Yeah, the Igor Labs guys, they collected a lot of data, but first of all, I noticed there were some errors in their data, which makes me not trust the rest of it, which is going to be a problem for anybody who tries to use my data too, because I'm not exactly like a university scientist that has their reputation at stake and all that. I'm collecting this data mostly because I want information on what makes for a good fan blade. A really quiet, high flow, high pressure fan blade for use in my big fan project, but also might as well collect some data for the PC fan filter box community. While I'm at it, I mean, data is data, right? So if I do a reasonably good job collecting the data, then that should be useful for that too. Yeah, so that's the story.